My name is Carl Kesselman. I am currently the William H. Keck Professor of Engineering in the Viterbi School of Engineering at the University of Southern California. I run the Informatic Systems Research Division at the Information Sciences Institute, which is part of the Viterbi School. And I have appointments as Professor of Computer Science and appointments in the Keck School of Medicine and the Ostro School of Dentistry. Prior to joining USC, I spent 7 years at Caltech as a Senior Research Fellow and a member of the Beckman Institute. And then before that, I was a member of the technical staff at the Aerospace Corporation in El Segundo. I did my PhD at UCLA in computer science. I have a master's degree in electrical engineering from the University of Southern California and a Bachelor of Science degree in electrical engineering and computer science from the State University of New York at Buffalo.
Wow, that's really impressive. So, how did you get interested in research in the first place?
Well, it was kind of an accident, I would say. I was interested in engineering and building things and making things work, and I didn't really want somebody to tell me what to do, and I kind of ended up falling into research. When I first came out to California, I wanted to get out of the snow of Buffalo and got accepted to get a master's in electrical engineering and was lucky to get hired by one of the founders of the internet at the Aerospace Corporation and in a research lab and just kind of fell into it.
So, in terms understandable to a high schooler, could you give me an overview of your research?
So my research has changed over the years, but right now, what I'm primarily interested in and primarily looking at, how do people use technology to collaborate together to solve really hard problems? So right now, we're looking at really hard problems in biology and biotechnology. And prior to that, we were looking at really hard problems in chemistry and physics and global change. It's actually a very old problem. If you look back in 1960, when computers were first coming up, there were these very prescient people who thought about, well, what are computers really going to be good for? This was before there were PCs and cell phones and things like that. And there was a demonstration actually in like 1962, which included interactive computing environment and a mouse and video displays and kind of almost in some sense everything we have today, but back then. So it's an old problem looking at how do we best use computers to do things that are going to be important. And I'm particularly interested in focusing on the role that data and knowledge plays and how people communicate and use data to communicate, and how do we do things that we know are going to be right. It's easy to produce. We see that now when you look in the newspaper and all these deep fakes and learning models hallucinating and things like that. It's really easy to produce the wrong answer, and it's really hard to produce the right answer. So how can we create systems that allow computers to help us solve really, really hard problems, get them right? And so that's really what my research is about.
That's really cool. And then, what were some of your most significant findings or publications?
I guess there may be a couple that I'm kind of pleased with. A number of years ago, we kind of came up with the idea as actually we're transitioning from the internet being a small thing to the internet being a really big thing, which happened around 2000 to somewhere around 2000, 2010, I guess. The web was really taking off then, and we were switching from a very small network. You used to get a list every month with all the computers on the internet. It was literally a file that had all the computers on the internet, and that was about 1982. And of course, now we're in this situation where you have no idea there's millions or billions of computers. So we thought about how do you tie together really big computers. At the time, they were really big computers, parallel computers with thousands of processors in them, or tens of thousands of processors. How do you bring them together and coordinate them so you can solve really hard problems? So we kind of created this platform, which eventually kind of became cloud computing, although not really our technology, but that kind of took over. But we were using large supercomputers all over the globe that we would coordinate to solve problems together. And me and a number of collaborators did a bunch of work in that and understanding how to build those. Ultimately, those ideas led to 3 Nobel Prizes. The computing work that we did went into that. So like the discovery of the Higgs boson which was this so-called God particle, and was posited that it existed many years ago. So they built a large experimental device at CERN, this particle accelerator, and all the computing to discover the Higgs boson was done on technology that we developed. More recently, I did some work, which is super cool, where we looked at how memories are formed in the brains of zebrafish. So we were looking at synapses, right, which is when your brain does something, a signal goes down a neuron, and then it gets to this kind of gap, and these chemicals leap over and they go to the other side. And it's how do those chemicals, the neurotransmitters, kind of go from one side to the other, and that thing is called a synapse. And we were able to develop a technique to actually measure where they were occurring in a living animal. And so we could look at how memories are formed. And so that was a pretty exciting piece of work. Yeah, and then I suppose way back, I did some really cool stuff where we were looking at communications and secure communications coming from the space shuttle. And we got called they had spent a huge amount of money, tens of millions of dollars, to get a contractor to try to sort out which messages were supposed to go where. And the contractor, the government, the Air Force wasn't sure they were doing the right message. Traffic was supposed to come down, and some was supposed to go to universities, and some was supposed to go to the Air Force. And they didn't want to mix those up. It was an early cybersecurity problem. And in the course of a couple of weeks, we kind of did everything the contractor did for tens of millions of dollars. And we were able to do that because we applied some very sophisticated programming techniques based on logic. There's a programming language, and this whole idea about how you could use logical proofs to program. And we use that approach, and we're able to do something that tens of millions of dollars in a defense contractor couldn't do. We did in a small number of weeks. And there's a lot of other kind of fun stuff I've done. But those are a couple of things off the top of my head that are quite different.
Yeah, that's awesome. So, what are the biggest challenges that you faced in research and how did you overcome them?
Kind of philosophically coming up with a problem that's meaningful and significant, and kind of focusing in and trying to figure out what's important versus what's not important. Identifying what's the right question is half the battle, or maybe more than half the battle. And then being smart enough to answer that question is also helpful. And then having the skills to do that. So, I would say kind of trying to figure out what's the most important problem, or what is an important problem that's worth spending time on. I think another kind of challenge in computer science and computing is that the technology changes so rapidly. So trying to get ahead of the change and not just be incremental, but really be ahead, and then just adapting. And then, at some point, everything old becomes new again as technology changes new things. So learning and keeping track, and then trying to figure out which of these things is just hype and is going to disappear in 6 months, and a lot of it does, and which is going to stick, and then how to actually be the person defining the thing that's going to stick rather than the thing that will disappear in 6 months.
So, in contrast to that, what do you enjoy most about your research?
I like building things that work. My research tends to be very multidisciplinary, so I do a lot of different things in collaboration with, lots of different people. So, and then the idea of solving interesting problems and doing that by making things work and getting people to work together. I think that's kind of the fun stuff. So you have something that, you put it together and the lights flash and it does what it's supposed to do, is always kind of fun.
Okay. And then, which person or mentor in your field has made the biggest impact on you?
I think I've been really fortunate that I've been able to work with a lot of interesting and pioneering people. So I'm not sure there's any one. I've just, had an opportunity to work and meet and learn from, many different people with many different skills.
And then, were there any pivotal moments in your research career that made you change topics or want to pursue a certain topic?
No one particular thing. I've tried to change what I'm working on over time. So what I do now is completely different than what I did my dissertation on. And I was thinking, my first published paper was actually in concert hall acoustics. So I've changed quite a bit over the years. So I think, being open for change is important, and figuring out how to adapt. Many years ago, looking at kind of the network and what was happening, and kind of this realization that this could be a big deal. I think, maybe also, I like to say, to annoy my friends, realizing that physics was easy and biology was hard, and kind of switching my focus from natural sciences to biological sciences. in my application domain. Maybe that was another big thing. Yeah, I suppose most of it has been kind of incremental, just looking at stuff and seeing things that are interesting and then following that.
And then I know like there's like a bunch of new technology and there's like all this AI now, but where do you see your research field expanding to? And what are some interesting topics that can be further explored within like the next 10 years?
Yeah, so this AI stuff is interesting. I think that there's actually some there. I mean, now I can say I've been around long enough where I've seen AI was going to change the world at least 4 times now. Well, actually, when I got started many years ago, there was this big logic programming and AI and rule-based systems based on logic programming were going to take over the world. And there was this big project called the Japanese Fifth Generation Project. And everyone around the globe was all worried about this. And the United States created their supercomputing initiative, and there's all this stuff going on. So, there's often kind of hype, and then you see, well, what's the reality of what's going to stick and what's just people making stuff up that actually doesn't work? I'll tell you two things, kind of one specific and more general, that kind of my big 5-year project that we're trying to put in place now. So I've been, as I said, really interested in this question of how do we use tools to put together solutions to challenging problems that we can verify that are true. You don't want to have a paper come out and then realize the data was wrong. And then could be profound societal impacts to something like a paper that says autism is linked to vaccines, even though it was clearly wrong. The data was terrible. The analysis was all wrong. The impact of that has been really dramatic. And I think people are starting to realize that much of what's coming out of all this AI is wrong. There's not enough attention being paid to getting the right answer or even understanding what the right answer is. So there's lots of that. So now, kind of with that as the background, I think that one of the really interesting things we're trying to put together now, which is kind of our 5-year plan, is looking at how do we build models that describe the behavior of a cell like in the human body. So how could we build computational and experimental models that allow us to understand what cells are doing, and then doing that in a context in which we can use that to drive new drugs, to drive new diagnostics, new all kinds of things to do that, but then also looking at kind of as a core part of that, let's make sure we get the right answers. And how do we enable other people to do new things and get the right answers? If we're successful in putting this project together, that's kind of what will consume my next 5 years.
Yeah, that's really cool. And then I know like in your introduction, you talked about how you were at Caltech for a while, but what were the different institutions that you've worked at and how were those experiences?
As I mentioned, I started the State University of New York at Buffalo. I did electrical engineering and computer science there. So while I was there, I spent a year at the Technical University of Delft in the Netherlands and did acoustics. That was fun. And then, as I had mentioned, I came to California and was at USC, UCLA, the Aerospace Corporation, and Caltech. Buffalo, I got a good education as to be an engineer without accruing a huge amount of student debt. That was good. When I was in Delft in the Netherlands, it was kind of my first chance of really working in a research lab and having to learn things on my own and actually running experiments. I sat there with microphones and speakers and computers and digital analog converters, and I ran experiments, and then that created a paper. Let's say at aerospace, I guess I was exposed to lots of new technology and people building and delivering large systems and kind of having to get stuff done, people expecting you to be able to do things and learn how to define and solve problems. Then at Caltech, it was being exposed to kind of an environment where everything is possible. You need to kind of create a vision and figure out how to execute on that. I would say at USC, it's been really about building teams and building things and learning how to network and interact with lots of people, and also really the opportunity. I had some of this at Caltech, but being kind of a bit of a smaller, more focused school, so it did mostly physics there and chemistry work. Worked with physicists and chemists, and then at USC, the opportunity to just do so many different things with so many different types of people. So I had large projects in geophysics, in global change, in cell modeling, in protein structures, and I mean, it's just kind of all over the place. I do a bunch of work in craniofacial dysmorphia. I'm starting to do some work in audiology. So just the opportunity to do lots of different things with lots of different people.
So, how did you find your passion for research, and how would you suggest a high schooler try to find their own passion?
As I mentioned earlier, I just kind of fell into it. So, the idea of making things work and trying to figure out your own path and solving problems, I suppose. In terms of what I would recommend for high school students, I don't get too focused too early. I, for example, say, well, what are the things that I call on every day? And, what I learned as an undergraduate, except for some recent hobbies where I've started playing with transistors again, everything that we learned is almost not relevant anymore. I mean, Ohm's law still works, that stuff, but all the technology is completely different. So I'm less concerned with whether you're an expert or even know Python or can program or things like that. Can you think creatively? Can you figure out how to ask questions? Can you figure out how to teach yourself? There's all these resources out there. Can you use them to learn new things? Can you take information and digest it? There's all these other skill sets which had nothing to do with science and engineering, which I found quite valuable. When I was in high school, I took studio art, and I had the instructor who was very big into art and aesthetics. And a good solution to a technology problem is a beautiful solution. And the same kind of aesthetics you apply to a piece of artwork or a building, apply to, is my program good, right? Yeah, it gets the job done, but it's ugly, right? So, how do you create things that have some kind of value and beauty to them? So things like understanding art and aesthetics. I gave a talk to a bunch of high school students a couple of years ago. I said, well, I'm a musician. I play chamber music. So I learned how to interact with people and how to take cues and when I should be playing together and when I should be playing differently, right? And how loud should I be, right? So kind of picking up these, maybe they're soft skills. If you understand how to approach a problem and decompose it and what's a beautiful solution versus an ugly solution and how to collaborate and work together, Python or not, I don't really care. You can always learn that stuff. Of course, it's good. You should understand mathematics and you should understand physics and chemistry and all that stuff. But there's a million people out there who do that and are really good at it. So, I think these other skills are important and valuable to have.
And then, what
Yeah.
kind of skills do you think that high schoolers could develop, even if they don't have access to an actual lab or any of like the tools that you have?
There's so much good free stuff that you could play around with as long as you have a laptop or a notebook or an iPad or what have you and access to the network. There's all these online tools for programming and exploration and understanding, how things work. I don't think you necessarily have to be exposed or spend time in a lab. I mean, if you can, that's great. That's invaluable, but I think maybe just getting kind of curiosity and figuring out what things are interesting to you and then trying to understand some of those things in non-superficial way is probably a good thing. Learning how to learn on your own, I think I find too often, even students in my class, it's like, why ask me? Figure it out the same way I did. Look at Stack Overflow, go to Wikipedia, learn how to read, right? Learn how to be critical against, okay, this says that, which is right. Can I understand this stuff? Oh, I don't understand that formula. Let me learn about what that formula actually is. In some sense, I mean, it's harder because there's a lot more things to know, but in some sense, it's also easier because you don't have to have a textbook to be exposed and learn about these things. That's a valuable skill to have that would serve everyone well.
Yeah, I totally agree. And then just for our final question, what type of advice would you give to a high schooler who's looking to get into research?
Learn to be curious, learn to try to understand answers, learn how to ask questions. If you could kind of hook in and if you're lucky enough to spend some time with somebody in a research lab or volunteering, that's probably not a bad idea. I would also say if you think you're interested in something that looks like that, then just look around, try to find things that you find interesting and you want to spend time on, like all of your time on. I mean, you shouldn't have to spend time on it. It should be, oh, it's now 2 o'clock in the morning. What was I doing? You can't force yourself to do that. So just don't worry, look around, try to find the things that are interesting to you and that you want to spend more time investigating. It's also worthwhile trying to find things you're good at. not everyone needs to do research or should do research. I mean, I thought for a long time I wanted to do digital signal processing, and then I discovered I wasn't very good at it, but I was really good at this other computer stuff. So at one point I said, well, I'm not going to do this anymore. I'm going to do what's easy for me and I'm good at rather than what's hard for me and I'm not good at. So try to find the things that you like to do that you're good at, that you want to spend a lot of time on it, and feel free to wander around. Don't feel like you have to pick something.
So that's all the questions that I have for today. And thank you
Okay.
so much for meeting with me.
Oh, you're quite welcome. Good questions.